Sounds great. I appreciate it, Rebecca. Thank you very much for hosting these workshops, which I believe are a very important way of communicating to a large group of people in a short period of time. As Rebecca said, my name is Phil Farina. I am the Midwest Business Development Manager for Clear Creek Systems, and as such, I am also the PFAS subject matter expert for Clear Creek, and have been following PFAS technology updates, rules, regulations, technology installs, review of the requirements for a number of years now. So I pretty much spend half of my day researching PFAS technologies, equipment, and looking at various medias and technologies that are available for PFAS treatment. As far as today's discussion is going to concern, we're going to be talking specifically about stormwater management and how to safely manage stormwater. I mean, there are many ways that we can manage stormwater. There's a lot of technologies available, but safety as well as compliance is extremely important. And sometimes a dollar spent on safety can rewards over something that is less expensive, but may not be as compliant and could potentially cause issues or damage. So what we want to focus on is not only compliance, but also safety. So a little bit about, oh, now it doesn't want to, there we go. I'm going to do a very brief overview of Clear Creek Systems, who we are, and what we do. And then we're going to kind of talk about a holistic approach. Many of the steps that you should be taking in a very specific order to help define your treatment system. And then we're going to talk about very specifically stormwater treatment theory, how it works, what to look at, what to stay away from, and why some of the analyticals that we're asking for are required and are helpful in treatment and design of stormwater treatment systems. And then we're going to spend a little bit of time on just the PFAS contaminant systems themselves and methodologies for treating PFAS. And one of the things that I continuously hear is that, well, there's no treatment for PFAS that's economical, that we can remove this material from the water. So why are we trying to do that? Well, hopefully at the end of this presentation, you will come away with at least PFAS treatment is imminently possible technologically. It is absolutely economical in its capability to remove PFAS from water. We can absolutely meet the current and potential future regulations for treatment requirements. And at the end of the day, it is extremely cost effective when you start looking at the 3 and 5 year cost of ownership of a project. Yes, on Monday, it costs quite a bit of money to put up a system, but once the system is put up and put up properly and designed properly, the operational cost of that system is very minimal. Therefore, over the course of 5 years, your cost per gallon treated is in the tenths or hundredths of a cent. So keep that in mind as we go down the line. As Rebecca said, if you have any questions while we're having the discussion, please write them down. I don't know if I'll see them or not, but Rebecca will definitely see them. She'll stop me and ask the question. So let's go on. A little bit about Clear Creek, a tiny bit of commercial interruption here. Founded in 1990, we have about 60 to 100 employees, depending on the number of projects that are happening. We have a lot of seasonal employees. for specific project areas. We do have nationwide service capability, although we have a significant number of our offices on the West Coast. We now have offices in the Midwest, particularly in Denver, in Toledo, Ohio, in Michigan. We have offices on the East Coast in Virginia and in Pennsylvania, and we have an office down in Texas. So we have the capability and the capacity to respond to treatment requirements nationwide. One of the things that separates Clear Creek from others is that we are a full service technology solutions provider, and we are technology agnostic. And what this means is we don't have a favored technology. We're not going to try and create a solution based on a technology that we have developed. We have access to all of the technologies. And as such, we are capable of putting in any type of a system that is required. What we say is the water, the flow, and the outcome, the treatment standard, that is what determines the treatment requirements. So when you're looking at a stormwater system, be cognizant of the flow rate, the analytical of the water, and the outcome that you need it to be, because that will determine specifically what your treatment requirements are going to be. Clear Creek has the capacity and experience with very large systems and very small systems. We can design, build, install, operate, purchase, to rent, any of these types of things that you need. Our goal is simple: to develop a strategic partnership to provide an engineered solution to solve the most complex water treatment issues. And we do that collaboratively, working with our clients, working with the regulatory environment, as well as working with consultants. We serve all of the markets. Predominantly, we see a lot of stormwater requirements on the West Coast, particularly in ports and terminals. Sand and gravel yards have a significant problem with stormwater. Timber facilities, particularly difficult water to treat, but we have developed technologies to treat that kind of water. Landfills, a lot of that water the stormwater goes through the landfill and comes out as landfill leachate. Very complex water, so something that you have to look at on a case-by-case basis. And then the petrochemical and PFAS remediation markets. The PFAS remediation could be drinking water markets or non-drinking water markets. All of our work that we are in is in the suspended solids, PCBs, oils and greases. We have capability of removing metals. We have a full house of chemical additives that may or may not be required to operate any particular systems. We can also do passive systems and active systems. We're seeing now passive systems in stormwater treatment becoming more and more interesting, because they're a little bit more expensive to install, but significantly less expensive overall to operate that system. So you don't need a lot of time spent with people involved in that treatment system. And then in the PFAS world, we have multiple sets of options for treatment. Hey, Wilson. And we're going to be doing that kind of a thing. Yeah, that's a good buddy of mine, Wilson Ruiz, from one of our very strong suppliers, Lanxess. So just wanted to welcome him personally. But anyway, I digress. What is important for you in defining your treatment system is what we define as a holistic approach. And it's really a moment to stop and say, what do I need to do before I start doing things? And by taking these steps, very specific series of steps, you can build that system correctly and succinctly for the specific needs that you have. So first and foremost, define the stormwater collection system. Are we talking about runoffs? Are we talking about a groundwater collection system? Are we putting it into ponds? Are we putting it into underground storage? Are we having vaults? Is it continuous? Is it something that is high volume? All of these types of things are very, very important because flow equals volume, volume equals size. If you have a very low flow rate, you can have a very small system. If you have a very high flow rate, your system gets to be much bigger and therefore can be much more expensive. One of the things to understand in that collection system is there's a trade-off between treatment size or flow rate and storage. Although storage is not completely inexpensive, it is significantly less expensive than building a very large treatment system. For example, if you have the capacity to store water, you can reduce your treatment system size to a couple of 100 gallons a minute instead of multiple hundreds of gallons. 8,000-9,000 gallons a minute is a large scale system. But if you have the capability of storing water for 2, 3, 4 days during a rain event, you can reduce that system, say, to 100 gallons a minute. Therefore, you may run it longer, but that system is much smaller, much easier to manage, and significantly lower cost. Once you've defined that water treatment system and have an understanding of what the capacity is of the water, you really need to look at the water from an analysis standpoint. And you should, at a very minimum, be looking at TSS, pH, PFAS. And if you're going to look at PFAS, you should look at speciation. By speciation, I mean, are we looking at PFOA, PFOS, PFBS, PFBX, PFHX? All of these different species have different application requirements. Some are long chain, some are short chain, some are branched, some are straight. Because of this differential, and by knowing the specific species that we're trying to remove, certain medias like short chain, certain medias like long chain, certain medias like straight linear materials, certain medias like branched materials. This helps us in defining the treatment system itself. While we're looking at analytical, we should look at the metals that may impact cadmium, chromium, lead, selenium, arsenic, all of these other metals. If you're building a treatment system for stormwater, you might as well take those out at the same time. It's also important because sometimes those metals will have an impact on the media that we're choosing for the PFAS species, for the PFAS removal, and therefore we want to take those out because they may compete and cause problems. Organics, of course, we know organics are very important because they have an impact on media, VOCs, and any other co-contaminants that may be in the water. The more complete the analysis, the easier it is to define the treatment system. Once we have that, we have to take a look at limits. Now, a lot of this presentation is going to be based on PFAS treatment, so let's talk about the limits right now. The federal EPA regulatory guidelines have not been established for stormwater. The states will have the capability to define stormwater limits until the federal EPA defines a specific limit for the non-drinking water applications. It's a little confusing at this point in time because the US EPA is currently focusing on drinking water, and that number is going to be 4 parts per trillion focused on PFOA and PFOS. That is going to, at some point in time, impact the PFAS limits in stormwater. Since stormwater does not directly go into the drinking water field, it impacts the drinking water field. For example, if you've got stormwater from a port and you're treating down to 70 parts per trillion, and that water is allowed to go into a river, that river may flow into a lake, that lake may flow into a pond, that pond may be used as drinking water. So even though it starts out as stormwater, there is a potential that stormwater can flow downstream and ultimately impact our drinking water. So what we're seeing now is most of the states have a number somewhere below 70 parts per trillion down to, in some cases, 7 parts per trillion. And we may see in the future numbers as low as 2 parts per trillion. So be aware that those limits are coming. We should also look at, yes, ma'am.
Bill, we have a question. What do you see as some key root causes for PFAS in rain? Is it burning plastics?
No, PFAS in rain predominantly comes from the fact that PFAS material can travel from a lake, a river, a pond that's been set aside in an industrial environment through the simple evaporation process. I took a group of students one time from the University of Massachusetts all the way up north into Arcadia National Park, and I asked the park ranger to take us to a tree that hasn't been seen by human beings for 100 years. We traveled for 3.5 hours. We got in front of the tree. I told the students to dig. We went down 3 inches, 6 inches, and 12 inches. And although no industry has been around there, all 3 of those soil samples had PFAS in it, and all were significantly above the background level. So how did it get there? Rainfall. So evaporation from any kind of a contaminated pond can bring that material up through the atmosphere. And in this particular case, because of the specific PFAS that was there, we tested it in Maine, and the material came from DuPont in Deepwater, Delaware. So it traveled over 700 miles. So it can get out there. And it's not through burning of plastics. Plastics really doesn't have that much PFAS in it. It's more the materials that are waterproofing agents, paper, the McDonald's wrap, so that the oil doesn't go through and make your hands a mess. Shoes and clothing, carpeting, landfill materials, all of those things have a lot of PFAS contamination to them. So unfortunately, it's in our rainwater as well as our drinking water, and probably in your hair care systems that you wash your hair with today. Once you have all of these concepts down, then you start looking at the equipment selection. Sometimes you need a temporary treatment system. For example, at a construction site, you're not going to build a permanent system on a 2-year construction site. You're going to put in a temporary system. But if you've got some kind of a port or an airport or a school or anything along those lines, you want to look at a permanent treatment system. There are some things that you can do with a permanent treatment system that you wouldn't do with a temporary treatment system, but there's also some things that you would do with a temporary treatment system that you wouldn't do with a permanent system, such as you might use carbon to use carbon for PFAS removal in a temporary system, knowing that the carbon is only going to last 3, 4, 5, 6 months, but the treatment system is only going to last 5 or 6 months. You wouldn't necessarily put in a ion exchange resin, which would last 14 to 18 months when the system is only needed for 4 to 6 months. By knowing all of these things in advance, it helps you define the process and therefore the costs. The flow rate, we talked about the flow rate a little bit. That has an impact on your system size. And then whether you want to do a regeneration of the media or replacement of the media. Regeneration might be in the carbon. You might use reactivated carbon. In a lot of cases for stormwater management, regenerated or reactivated carbon is sufficient. In the other medias, organoclay and ion exchange resin, the process for regeneration isn't really effective and efficient. In the case of ion exchange resin, it requires methanol. It's not something that you want to be doing on a consistent basis. So for regeneration, you would look at the granular activated carbon or coconut carbon. And we'll talk about those things in a minute. Okay. Issues that affect stormwater management. Flow rate. Typically, stormwater scenarios have a very, very high variability, and they're very intermittent. You don't really see rain every day, unless, of course, you live in Seattle. You don't really see rain all the time every day. So that treatment system will see a jump in treatment requirement and then a drop off. This is why we talked about storage. If we can level that out and make it more equal over the course of time, you can have a lower cost treatment system. Another important piece of the puzzle is, where is the treated water going to go? If it's going to a river or a lake or back underground to a POTW, to a stormwater system, all of these have specific permit limits and permit requirements. One of the things I always advise in any of these project types, treat to the permit. If you don't have to get to non-detect on a contaminant, treat to the permit. By doing that, you can keep your economic in an area that you can handle. You can keep your treatment size and design to something that can basically fit your footprint, and you're still doing the right thing. So knowing what your permits are, knowing your permit limits is extremely important in defining your total treatment system. When you start looking at the contaminants of concern, the things that negatively impact any treatment system is TSS and TDS. If you have a media and you have high TSS, that media can drastically shorten the life cycle of that media. So we need to know that. We need to understand that suspended solids. Sometimes that suspended solids could be clays and silts. Those are very difficult to manage through simple filtration or settling. So it's important that when we're evaluating for suspended solids, we understand the particle size and the physical makeup of that material. I know it sounds like we're doing a lot of extra things, but by doing it right this way, we don't have any disappointments downstream, and we don't have to adjust anything by trying to put something in the middle of a treatment system that wasn't designed properly. Oils, greases, hydrocarbons, and VOCs. Oils and greases, again, can very negatively impact your medias. Hydrocarbons and VOCs, by knowing which ones they are, we might be able to define an organoclay for certain hydrocarbons. If there's metals in there, we could use an organoclay. If there's volatiles in there, such as diesel or gas, we can use a carbon, maybe even a reactivated carbon, maybe a carbon and organoclay blend. By knowing these things, again, we can define that treatment system. PFAS, you really can't say enough about PFAS. It is going to become something that is going to start appearing in a lot of the permits. So it is something that has to be managed. And like I said, it's extremely valuable to do a deep dive analytical on the PFAS to know and understand the speciation of that material and whether the specific species involved is on your permit or not. PFAS is about 6.5 million chemicals come under the nomenclature of PFAS. There's no way we're going to be treating for all of those, and there's no way you're going to be analyzing for that number of species. The US EPA recommends 29 specific species of PFAS that should be looked at when you're developing a treatment system. These are well known in the analytical world, and they are the analytical capability is very good to be able to determine how much of these 29 specific elements are in your water. So by doing that 29 species analysis and all of the rest of the analytical, you will have a very good opportunity to define your treatment system. Limited footprints. Yes.
We have a quick question, just clarification. What is the difference between reactivated carbon versus activated carbon?
Okay. Granular activated carbon is a specific material that frequently is coal sourced, and the activation process is one in which the pores within the granules themselves are opened. When these pores are open, it allows the adsorption, which is the surface capturing. Think of a V. If something comes floating by in that V and it gets entrapped in that V, that is adsorption. So by opening these funnels, if you will, or entrapment zones, that allows you to have more capability of entrapping the contaminants of concern. Regeneration is the application of heat and pressure to the exhausted carbon in order to remove these entrapped moieties and destroy them in the heat and pressure process. For example, all of your organics can come out that way. All of your PFAS can be removed from carbon in that fashion. So you're basically entrapping the contaminant and then sending the material off-site to be processed in the regeneration process. That material can then be resold as a regenerated or secondary use carbon. Part of the associative problem with that is it does change the nature of the carbon molecular structure itself. You do get some ash is formed, around 15 to 20% ash is formed, so you have to replenish that. The regeneration process closes those capture points, so you have to reactivate those capture points. So there's a multi-step process there, and it's not quite as effective as virgin material. But again, if we have a short-term project, couple of months, we don't have a lot of contaminants in it, we can utilize that regenerated carbon, which is significantly less expensive than virgin carbon. It will exhaust quickly, but the process is over quickly. So by knowing all of these things, you can choose the right material. Another thing that you have to worry about in PFAS or in stormwater management is your footprint. The equipment for large scale volume flows is pretty big. You know, you can have 5, 6, 7 tanks, you can have some vessels, you can have some pumps, you can have a lot of different things. If you have a very tight footprint, we need to know that to help define that treatment system. Because all of the components are individualized, you can lay them out in various plans. But we also have the capability of compartmentalizing treatment systems. For example, I know you're all familiar with Connex boxes. You can put an entire treatment system for a stormwater event inside of a Connex box. You're only going to treat 50 to 100 gallons of water a minute, but if you have significant storage capability, a 40-foot Connex box is sufficient to treat 100 gallons of water a minute from a storage event. you treat it over a week or 10 days, you have treated a significant amount of water each day. So again, storage versus treatment size, they can go hand in hand in developing a treatment system that is economical. And then a permanent system or a temporary system, and we talked a lot about that already. So what are the treatment steps? Okay. The treatment steps tend to be chemical precipitation. Chemical precipitation may be the addition of a flocculating agent, a coagulating agent, in order to take materials that are floating throughout that water, TSS, and drop them out of the water. With chemical precipitation, you're pretty much focusing on heavy metals and solids. If the heavy metals are soluble, then you require the next step, pH adjustment, and we'll talk about that in a minute. But for chemical precipitation, you flocculate these things, you precipitate them out, and then your removal mechanism would be filtration. So chemical treatment, filtration go hand in hand. If you have materials that are soluble, by adjusting the pH, either up or down, depending on the solubility and what you're looking at, by adjusting the pH, you can take a material that's soluble and make it insoluble. Once it's insoluble, you can precipitate it out, and then you can filter it through standard filtration measures. But if you adjust the pH at the beginning, somewhere at the other end, you're going to have to adjust the pH again in order to be in that 6 to 9 pH range. In some cases, if you only need gravity settling, and these are to remove heavier or larger particle size. You know, a lot of times when water hits the roof of an asphalt roof, you get all of those little pieces of asphalt that come off. Those will settle. They'll fall to the bottom, so they don't become involved in the treatment. You might see that in a ditch, where if you're sucking the water out of a rain ditch or out of a cement vault, there might be leaves and dirt and gravel and other things in there. They just settle by gravity. But that also means at some point in time, whatever you're using as your settling step, that's going to have to be cleaned out, and those solids are going to have to be disposed of at some point in time. We mentioned filtration. Filtration is going on after any suspended solids. Straight filtration will not do anything to remove soluble materials. It has to be insoluble in order to remove suspended solids. And those materials will come out, they will be either through a sand filter, they will come out as a sludge, or through a bag filter, they will come out as exhausted bags. These things will have to be disposed of. So you're going to have secondary items to dispose of, or secondary waste streams that will have to be disposed of. And then media. Media could be organoclay, carbon, resin. It could be any number of other types of alumina, iron, other materials that are dependent upon what is in your stream. And these are going after the dissolved contaminants, the PFASs, the hydrocarbons, the VOCs. There you're going to get either absorption, which is the mechanism in which the contaminant goes inside the media like a sponge. You can have adsorption, where it gets entrapped on the outside of the media. Or you can have something called ion exchange, where you're going to give up something like a chloride ion and create an active site where something like a PFAS will attach to that ion exchange media, and that is how it is entrapped. Some medias use all three mechanisms, some medias use one mechanism, but in any event, all of that media at some point in time will also become a waste, and it will have to be disposed of. So unfortunately, just treating the water doesn't get you out of the treatment train concept where you're going to have some other waste streams along the way that need to be dealt with. So let's look at some pictures and some ideas of what treatment systems look like. What you're looking on the right is a stormwater treatment system that was designed for a dewatering or construction dewatering scenario where the water is captured in a pond, a purpose-built pond, and then any dewatering activities that take place are also sent to that pond. That water goes into those two great big orange containers. Those containers allow for the settling and the addition of polymers, etc. Goes through those blue sand filters and then out the door. So here we have the chemical treatment and the filtration type of a system. You can have bag filters, cartridge filters, sand filters, oil and water separators. All of these types of technologies are all available and are necessary to get to a treatment system that meets all of those permit requirements. Different types of media that may be employed. You can have carbon, organoclay, ion exchange media, and blends. Which one do you choose? Well, we've done the analytical up front. By having that analytical, we know which of the medias to choose for specific components within that contamination stream. If you have metals, we can use resins, zero-valent iron, activated alumina, or in rare cases, reverse osmosis. One of the reasons why you don't want to do reverse osmosis, if you can avoid it, it's marginally expensive and it creates a significant waste stream, which is the reject water from the reverse osmosis process. And in many cases, that can be hazardous material. We don't want to take naturally occurring rainwater and convert it to a hazardous material if we can avoid it. Typical types of systems is you have a filtration pod. That's those great big orange pods there. You have the water storage, which are those white vessels there. And then you have other filtration and component parts inside that blue box. So this is a 150 gallon a minute to 200 gallon a minute treatment system. As you can see, it's not extremely complex, but it is well designed so that we know what is going into it. And on the right, you can see the storage pond where a significant amount of water can be stored so that treatment can be accomplished over a longer period of time rather than trying to put in a 2,000 or 3,000 gallon a minute treatment system. We've done it, but they're very expensive. Let's talk about PFAS for the last 20 minutes. PFAS is the poly or perfluoroalkyl substance, better known as the forever chemical. It does not have to be a forever problem. There are technologies, there are methodologies, there are methods to remove it. Let's look at it in the light of stormwater. Where would we find this material? If it's raining near an airport, an industrial site, you're going to have a chance of having PFAS in that water. If you're dealing with a well water nearby, if that well water is contaminated, a landfill, a transfer station, somebody's lift stations from stormwater contamination, you're going to see it there as well. Paper production sites, logging facilities, all of those sites are all going to see a potential for PFAS. And literally, if you look for it in the rainwater, 90% of the time, it's going to be there. So it's not something, oh, I'm dealing with rainwater, I don't have to worry about it. No, it's in the rainwater. Treatment systems for PFAS, there are a multiple number of technologies that are coming along, but they're not commercialized just yet. The commercialized systems to remove PFAS are basically media systems. You have other commercialized treatment systems, such as foam fractionation systems. Foam fractionation systems are excellent, but they tend to be used on a continuous treatment system. they may or may not be specifically applicable to a stormwater system. So we're not going to spend a lot of time discussing treatment systems that are not directly applicable to what we'll call intermittent treatment. Organoclay, carbon, and ion exchange resins are very effective in the intermittent treatment type of system that you might see in a stormwater system. Carbon. Carbon is an extremely well-known material. In the case of carbon, you can have virgin carbon, reactivated carbon, and we talked about that process. You can have carbon that comes from mined carbon, which is bituminous carbon. You can have carbon that comes from wood. You can have carbon that comes from fiber. You can have carbon that comes from coconut fiber. But functionally, when you're dealing with PFAS, the carbon that you want to use is virgin, mined, bituminous carbon. Other carbons will work, but not for long periods of time and not for significantly low levels of PFAS treatment. But again, we've done the research. We know the analytical. We know what's happening. If it's a short-term project, doesn't have a lot of PFAS in it, we may be able to employ a non-bituminous carbon source. Organoclay. Organoclay is a surface-modified, naturally occurring material that allows the PFAS material to become adsorbed to the outside and absorbed to the inside of the structure. And there's also some ion exchange application as well. So you have 3 different mechanisms that are taking place, and therefore it can retain significantly greater amount of PFAS in the treatment system, and thus you might be able to use a smaller treatment system. On a per dollar basis, it may appear to be more expensive. But when you're looking at the overall cost of ownership, your vessels are smaller, your footprint is smaller, the amount of media you need is smaller, the amount of time that the media will last is much longer. So at the end of a 3-year period of time, organoclay can become significantly more cost effective or cost efficient than a carbon treatment system. So again, knowing how long your system is going to last has a direct impact on what media you're going to choose. Ion exchange resins, these are man-made materials designed very specifically for PFAS treatment. If you're using an ion exchange resin for arsenic removal, it's not the same material. These are extremely specific. You can use these instead of carbon. You can use them instead of organoclay. You can use them in conjunction with carbon or in conjunction with organoclay. They like the long and the short chains better. They have the adsorption mechanism, the absorption mechanism, and the ion exchange mechanism. Again, you use a much smaller quantity of them. They react much faster. The footprint of your system can also be much smaller. So there's a lot of opportunity there. Sorry about that. Where did it go? Oh my God, we lost it. Hang on a second. Anybody know how to get back here?
What's going on, Phil?
Can you still see my slides?
Yep, we can still see him.
Oh, okay, fine. So the ion exchange resins can be very effective depending on the type of material that you're trying to remove and how long you're working on removing that material. So we talked a lot about carbon. Basically, it's the lowest cost initially, but it may have a higher cost overall. It does exhaust relatively quickly. So you will have to have material coming in and going out quite often, maybe 3, 6, 9 months before you have to dispose of the material. Disposal of the media is very simple. Either landfill or incineration are the typical methodologies for disposal. There are technologies to renew or revitalize or regenerate that carbon. But if you get a short-term project, that's the place to go. It does have a high flow-through capacity, and it does, however, require about 20 minutes empty bed contact time. And what that means is if you have a high flow volume, you're going to have larger vessels. And the bed life is around 50,000 bed lives, which is 8, 9, 10 months before the material is exhausted. This is a typical type of a system. You have your primary treatment up front. You have your lead lag type of a system. And the reason you will see this lead lag concept in all of the medias is because the lead vessel is going to do 95% of the work. The lag vessel is going to be a polishing unit to the lead vessel. Well, why do I have it there? As the lead vessel begins to get exhausted on any of the medias, you will start throwing some of the material off the lead vessel. It goes into the lag vessel. The lag vessel captures it. Think of a 5-gallon bucket of ping pong balls that can hold 1,000 ping pong balls. In your 50, 60, 70, 80, 90, 500, 700, 800 ping pong balls, they're all falling into the bucket. Nothing's coming over. As you start getting to that 850, 900 ping pong balls, as you drop them in, sometimes they bounce out and go into that second bucket, but they didn't leave. They were captured. As you get higher and higher in that number of ping pong balls, you start spitting out more and more ping pong balls, but you do retain some. So this allows you to take that lead vessel and that expensive media and run it longer so that you're getting the most bang for your buck out of that media. When you change out your media, you are not changing out both vessels. You're only changing out the lead vessel. You're going to flip some valves. The lag vessel will now become the lead vessel. The lead vessel becomes the lag vessel, and you go down the path again for another 50 to 60,000 bed volumes. Organoclay, it is a naturally occurring material. It has a very high working capacity, which means it can take up a lot of material. It also removes a wider variety of PFAS materials, predominantly the long and the short chain. But where it has an advantage, it's a 5-minute empty bed contact time. Carbon, we said, was 20 minutes. Much smaller system, much faster system, much less media, lower cost over the course of time, but maybe a little bit more expensive on day one. It lasts much, much longer. If you remember, carbon was 50,000 bed volumes. This could be upwards of 300,000 bed volumes, significantly longer period of time. But again, you have to have that pre-filtration system up front. That's very important. Money spent on that pre-filtration system significantly improves the life expectancy of any of the medias. So we will always spend the time to look at what do we need to do to protect that media, because you don't want something going in there and shortening the life of a media that's very expensive. You want that media to last as long as possible. Ion exchange material or ion exchange resin, we talked about man-made. It has a multiplicity of methodologies of absorption. You can reach extremely low levels of PFAS into the non-detect level, much less media change out because it lasts so much longer. 350,000 bed volumes to 700,000 bed volumes, not unusual. Much faster reaction time, 2.5 minute empty bed contact time. Back to smaller still, less media, very competitive. If you have a long-term treatment system, the organoclay and ion exchange medias can be very, very effective in keeping your entire cost of ownership much lower than it would be if you put in a system that was built on the cheap to begin with, but you may have to have a significantly greater number of media changeouts. What does it look like? Same as the other one. Filtration system or primary treatment system, followed by a lead lag, all for the same reasons. So if you're going to look at a stormwater treatment system, take the time to look at it from an entirety or a holistic approach. Define that collection system, understand the water chemistry, define the specific outcomes of the project, where the water is going to, how much water you have to treat, and then work with someone who's collaborative, has a background in all of the technologies, has an understanding of size limitations, economics, safety, and outcome. And we hope you would consider that Clear Creek is that organization to work with, because our goal is to be your partner in stormwater and PFAS remediation. So that's my presentation. I pretty much nailed it, Rebecca. I got to the 4:50 or what over here in Ohio, it's 4:50 p.m. So there's 10 minutes for questions. If anybody has any questions, I'd be more than happy to try my best to answer them.
Fantastic. Thank you, Phil. And if you have any questions, go ahead and put them in the chat and we can get those answered for you. But this is so great information and we're so thankful for Phil for joining us. Like I said earlier, for those that joined a little bit after we started, this was recorded and it will be posted on our website. So if you missed any of it, you can watch it again. It'll be available between 24 to 48 hours for free, as well as all the other workshops that are happening during Stormwater Awareness Week. So be sure and check that out. And we have one more online workshop for today, which is America's Proven First Line of Defense for Stormwater Runoff Pollution Abatement. That starts right at 2 o'clock, so in about 10 minutes. You can join that, so be sure you're registered for it. But it doesn't look like we have any more questions, so we might let everyone go. But thank you so much, Phil, and thank you for joining us, everyone.
Thank you.